Sawing marks the first step at Bruck's facility, where 18 industrial saws operate non-stop. Materials up to 2,160 millimeters diameter are cut, labeled, and sorted immediately. At Bruck, the production of seamless hot-rolled rings and custom forgings starts with the transformation of raw steel into massive blocks. These are heated in high-capacity furnaces before being moved to hydraulic presses, where forming takes place under immense force. The red-hot billets are shaped into rings or flanges based on customer specifications or industry standards. After forming, each piece is precision rolled to ensure dimensional accuracy. Surface imperfections are removed before moving on to subsequent processing steps. Advanced cooling systems and controlled environments ensure material integrity. Non-destructive testing, such as ultrasonic inspection, verifies structural soundness. Components then undergo heat treatment for enhanced strength and durability. Additional inspections are conducted post-treatment to confirm compliance with tight specifications. CNC machines perform finishing operations, from drilling to contouring with tight tolerances. Each part is tracked with digital labels throughout its journey. Bruck's integrated process allows them to deliver high-performance parts to sectors like energy, shipbuilding, and heavy machinery. The DB12500 CNC crankshaft grinder is engineered to handle some of the largest crankshafts in the industry, accommodating workpieces up to 12.5 meters in length and weighing up to 25 tons. Its robust double-base structure and hydrostatic guideways ensure stability and precision during the grinding process. The machine's orbital grinding system, controlled by advanced CNC software, allows for the simultaneous machining of main journals and crankpins without the need for indexing or additional counterweights. Equipped with a 2,000 mm diameter CBN grinding wheel and in-process gauging systems, it achieves high accuracy and surface finish. The DB12500 is particularly suited for applications in marine, energy, and heavy industrial sectors where large-scale crankshafts are common. Its design emphasizes efficiency and precision, making it a valuable asset for manufacturers requiring reliable and consistent crankshaft production. Designed for machining large, complex components, the ACCUWAYUT400 lathe combines power, precision, and structural stability. The process begins with a single-piece mehanite casting base, reinforced with heavy ribbing for rigidity. Each unit undergoes individual dynamic balancing of all moving shafts and gears before installation. The two-step gear spindle, integrated with helical gearing, delivers high torque output while reducing noise and backlash. A slant bed with heavy-duty boxways supports smooth, multi-axis cutting operations. ACCUWAY's power turret includes dual motors, one for tool disc rotation and the other delivering 11 kilowatts for driven tools, outperforming standard VDI designs. Tool changes and heavy cuts are executed seamlessly. Tailstock options include MT5 live center or rotating quill, with the choice of a belt-driven subspindle for additional flexibility. The machine supports cutting lengths up to 3 meters. Hydraulic steady rests can be added to stabilize long, heavy workpieces and prevent deflection. Together, these features ensure that each phase of production upholds the high standards needed in the aerospace, energy, and heavy industry sectors. A massive 120-ton forged workpiece is mounted onto the rotating table of a CNC double-column vertical lathe. Machining begins with outer diameter cutting and profiling, followed by facing and chamfering. The vertical setup and dual-column structure provides stability in access, enabling precise shaping of large industrial components used in heavy-duty applications. Machining a chest rook from solid aluminum begins with securing a 2.5-inch diameter 6,061 bar stock into a CNC turning center. The Mori Seiki NL2500 SY700 uses its Y-axis, C-axis, and live tooling to execute multiple operations in a single setup. The outer profile is first shaped using precision turning tools, gradually refining the contour. Live tooling then engages to mill the slots and details around the rook's crown, features that would be difficult to achieve with turning alone. The C-axis allows synchronized rotation for accurate alignment during milling, Throughout the process, coolant floods the cutting zone to reduce heat and remove chips. The Y-axis enables off-center operations, adding complexity and symmetry. After turning and milling, the part is parted off and collected. This hybrid machining process minimizes manual intervention and ensures dimensional consistency. By combining multiple axes and tools, the machine delivers a fully finished chess piece with sharp definition and a smooth surface, ready for polishing or display straight from the lathe. At Schaeffler's Indian facilities, bearing production begins with precision heat treatment of inner and outer rings. These components are then ground, honed, and assembled into various bearing types, such as spherical, cylindrical, and tapered roller bearings. Plants in Malaysia and Savli operate high-precision machines developed in-house, based on German engineering. Every stage, from machining to final inspection, is subjected to rigorous quality control. These facilities supply robust components for railways and heavy industry, ensuring durability and reliability in critical applications worldwide. The Master G8812 engine is assembled by skilled technicians who personally ensure each component meets high standards. After careful inspection, the engine undergoes rigorous cold and hot testing. An infrared defectoscopy ensures flawless performance. Designed for gas-powered generators, it delivers reliable power for industrial applications. A massive HS500 steel plate undergoes heavy milling with a 3-inch ISCAR 490 cutter. The machine removes material at a 0.5-inch depth, spinning at 360 revolutions per minute and feeding at 13.4 inches per minute. Despite harsh conditions, tool life exceeds 45 minutes, showcasing remarkable endurance. This heavy-duty CNC lathe handles massive workpieces up to 1,620 millimeters in diameter, 7,000 millimeters long, and weighing 48 tons. It performs rough and finish turning, profile shaping, corrugation cutting, and thread machining. Equipped with a milling unit, faceplate rotation, and automatic tool calibration, it's built for high-precision, large-scale operations across various metal alloys. High-pressure hydraulic cylinders begin with precision machining of piston rods and tubes. Parts are honed, assembled, and tested to withstand pressures up to 700 bars. With strokes up to 8,000 millimeters and up to 22,000 millimeters via partnerships, they're built for demanding applications. Rhombic and lentil cutting ensures exact profiles for support rolls and shaped rolled products. Massive stamping presses shape thick metal sheets with immense force. A 2,000-ton Bliss and an 1,800-ton Versen press handle high-volume forming, producing structural components for heavy industries with extreme accuracy. Each Morse taper twist drill undergoes a series of intense transformations. The making of a Morse taper shank twist drill begins with rolling forge machines shaping raw steel into blanks. Tip sections are cut, then ground to form the initial cutting geometry. Lathe turning and snagging refine the body, followed by polishing for a smooth finish. Heat treatment hardens the material, enhancing durability. The shank and cutting edge are then accurately ground to meet precise tolerances. Finally, the drill point is formed and marked by rolling. Each step contributes to producing high-performance tools capable of withstanding industrial demands. In this video, you'll see how Estwing's iconic hammers, axes, and specialty tools are forged to perfection. Each hammer and axe starts with premium American steel, carefully forged to perfection. The tools are then thoroughly shaped and polished, with each handle receiving the patented shock reduction grip. After assembly, each tool is inspected for durability and performance, ensuring it's ready for use in any tough job. At XR, part of the production process involves forming secure terminations on specialized pull lines. One end of the cable is bent into a loop and threaded through a pre-drilled metal component. A curved metal insert is then positioned inside the loop to distribute tension. The free end of the cable is pulled tight, locking the loop into place around the insert. Finally, a metal sleeve is crimped over the loose end to secure the assembly. This method ensures strength and safety under high tension, making the cable suitable for critical load-bearing applications. For this 20-meter railway girder, Flux-cored arc welding fuses massive steel plates into a single beam. Sections are joined in stages, with multiple welders operating simultaneously to ensure structural integrity and consistent penetration throughout the span. The MC650 tube and profile bending machine is engineered for precision and versatility in shaping metal components. Constructed from welded and machined steel, it ensures durability and stability during operation. Equipped with 3 traction rollers, it can bend round pipes up to 4 inches (1.6 millimeters) in diameter without damaging the material's surface. The machine operates in both vertical and horizontal positions, accommodating various workpiece sizes and workshop layouts. Its electro-hydraulic system, powered by a 3 kilowatt motor, delivers consistent performance. The MC650 features an intuitive control panel with 4.0 technology, allowing operators to program and store up to 10,000 bending sequences for mass production. The independent adjustment of the lower rollers enables tighter radii and improved material utilization compared to conventional pyramid-style benders. This setup is ideal for manufacturing components like flanges, railings, and structural elements used in construction and urban infrastructure. With its robust design and advanced features, the MC650 enhances efficiency and precision in metal fabrication tasks. This manual tube bender, model TM025, shapes round and square stainless steel tubing with ease. It handles gauges 16, 18, and 20, using a hand crank mechanism to apply uniform pressure along the bend. With adjustable dies and a solid frame, it delivers clean, consistent curves without collapsing the material. Ideal for workshop use, it gives operators precise control over the bending angle and radius. At the Ithaca steel mill, production begins with raw materials processed in a blast furnace, followed by continuous casting into slabs. These are reheated and rolled into coils through high-pressure rollers. Advanced automation ensures thickness uniformity and surface quality. Each stage, from melting to coiling, is optimized for high efficiency, supporting large-scale construction and industrial applications. High-speed precision meets heavy-duty metal forming in this double-action cupping press. Designed for blanking and cupping operations, the process begins with a metal strip fed continuously into the press. A top punch performs the blanking, while a lower die shapes the cup in a single synchronized cycle. The double-action design enables smooth material flow and reduced deformation during deep drawing. Sensors monitor alignment and pressure in real time to ensure consistency. Each cup exits via an automated chute ready for further processing. This setup is ideal for producing metal cans, shells, or components that require both speed and structural integrity. From flat sheet to finished duct, this fully automated line handles every stage. It begins with destacking and double sheet control to ensure only one blank enters at a time. Edges are prepared before infeeding into the manifold system, which can produce 2- or 4-fold tubes. A 2-roll bender shapes the sheet, followed by laser welding using a trump source. The seam is then planished for a smooth finish. Next come annealing and calibrating processes to refine structure and dimensions. Finally, the tube is expanded to meet specifications, round, oval, or rectangular, ready for industrial use. Inside the bus kneader system, polymers, fillers, and additives are fed through multiple intake ports. The screw shaft performs both axial oscillation and rotation, creating a distinctive kneading motion. Fixed pins along the barrel enhance mixing by directing material flow. As the compound travels, liquid additives are injected in timed intervals, and gases escape through ventilation outlets. A restriction ring ensures materials remain in the melting zone long enough to fully fuse. Degassing units extract steam and volatiles to improve product purity. Internal temperature sensors continuously monitor the process to maintain optimal thermal conditions. Transport and kneading elements alternate to balance shear and mixing efficiency. The 4-flight screw design in Quantec G3 and MX models improves processing for heat and shear-sensitive compounds. This setup supports the production of high-performance formulations used in advanced industrial applications. The production of cast iron bathtubs begins with crafting sand molds, precisely shaped to match the final design. Molten iron is poured into these molds and left to cool and solidify. Once hardened, the mold is broken, revealing the rough casting. Excess material is removed through deburring and trimming. Surfaces are then inspected and refined to ensure a smooth foundation for the enamel. The bathtubs then undergo a second enameling process, where a durable glass-like coating is fused to the surface for protection and appearance. This coating is applied electrostatically and fired at high temperatures. After quality checks, the finished products are carefully packed for shipment. This process combines traditional casting techniques with modern finishing technology to deliver robust and hygienic bathware. Inside the foundry, a worker loads wet scrap metal into the furnace. This step is essential to melt down scrap and begin the metal recycling process. As moisture contacts the molten surface, intense bursts of steam and sparks erupt. It's a dangerous moment. Any trapped water can flash to steam and explode. The copper ingot casting process begins with molten copper being transferred into a casting system. Molten metal flows into molds aligned on a conveyor. As the ingots cool, they gradually solidify while moving forward. Once fully formed, they're removed and stacked for further processing or transport. This continuous casting method ensures consistent ingot size and efficient output. Molten aluminum is poured into a permanent metal mold to produce durable pans like tawas. The process begins by preheating the mold and applying a coating for smoother release. Once the aluminum reaches casting temperature, it's ladled into the mold cavity. After solidification, the mold is opened and the rough pan is removed. Excess material is trimmed, followed by grinding and finishing. Holes are drilled for handles, and surfaces are polished for a smooth finish. This method offers superior strength and repeatability, making it ideal for mass production of cookware. In this video, you will witness the full repair process of an electric motor, ensuring it performs at its best. The procedure begins with Megger and surge tests, checking insulation strength and electrical integrity. After disassembly, defective parts like bearings and windings are replaced, and the stator undergoes a burn-off process to remove old windings. The coils are then carefully wound and installed, followed by a series of inspections and retesting. The motor is baked, dipped in varnish for protection, and balanced to precise specifications. Once fully reassembled, it undergoes a full-load dyno test to ensure it meets performance standards. The process concludes with a fresh coat of paint and a final quality check, preparing the motor for delivery. What makes the CFM 56-5B the trusted engine behind the Airbus A320? It starts at the fan, where incoming air is divided. Some bypasses the core for thrust, the rest enters the compressor. Air is compressed through several axial stages, reaching temperatures up to 450 degrees Celsius. In the combustion chamber, fuel is added and ignited, spiking the temperature to nearly 1,700 degrees Celsius. This high-energy flow drives the turbines, which in turn power the fan and compressor. The engine converts intense heat and pressure into forward thrust, offering high efficiency and reliability on every flight. Designed for rapid lifting, the Autolift 3000 raises vehicles up to 60 centimeters in just 25 to 30 seconds. Powered by a drill, ratchet, or hand crank, it's lightweight and highly portable. Ideal for 99% of vehicles under 3,000 kilograms, it allows easy access for inspections and repairs. The compact design makes it suitable for garages or laundries, where fast undercarriage access is essential. Carbon unloading begins with transferring material from bulk trucks into a sealed receiving system. A dust-controlled conveyor moves it to the packing station. There, operators insert heavy-duty bags into discharge nozzles of the filling unit. Once filled, the bag is immediately sealed to prevent dust escape. This closed-loop process ensures both safety and environmental compliance while preparing carbon for storage or further processing. When a 293-meter cruise ship like the MSC Magnifica enters dry dock, The repair process is a race against time. After arriving at Damen Ship Repair, Rotterdam, she's supported by hundreds of dock blocks as the dock is drained. With 700 crew members still aboard, auxiliary engines keep utilities running. Crews immediately begin replacing 40 tons of steel, repainting over 6,000 square meters of hull, and removing old rudders. While mechanical teams prepare new rudder stocks in an on-site workshop, lifeboats and davits undergo inspection. Stabilizers, thrusters, anchor chains, and bearings are serviced, with some parts cooled in liquid nitrogen for fitting. Anti-fouling coating is applied, and polished propellers enhance efficiency. A day ahead of schedule, lifeboats are reinstalled, freshwater tanks refilled, and the vessel departs, restored and ready for her next journey. Off the coast of Venezuela, the anchor-handling tug supply vessel Boulder plays a vital role in stabilizing offshore operations during the Perla project. In this operation, Boulder supports the lay barge, Castoro 7 inches, by deploying and retrieving anchors used to position the barge precisely for subsea pipeline installation. Each maneuver is executed with coordination between deck crew, winch operators, and bridge officers. Massive anchors, often weighing several tons, are hauled on board using heavy-duty winches and guided into position via stern rollers. Once secured, the anchors are released at predetermined coordinates, ensuring the barge remains stable during pipelaying. This task demands constant communication between vessels, especially during shifting sea currents. Timing is critical, as delays in anchor deployment can impact the entire pipelaying schedule. To minimize risks, crews perform repeated checks on gear integrity and positioning data. The crew must monitor tension, adjust wire angles, and account for weather and sea conditions. Specialized tools, such as shark jaws and towing pins, help manage the mooring lines during operations. Accuracy is key. Errors in anchor placement can disrupt the entire pipeline trajectory. After laying the pipe section, Boulder retrieves each anchor, sometimes repositioning them as the barge moves forward. The entire process is repeated multiple times, requiring endurance and precision from the crew. Every anchor handled is a step toward completing vital energy infrastructure beneath the sea.